Okay, so today I want to talk about rainbows, and everyone's seen rainbows, everyone is aware of what they look like, everyone has a vague idea of what's happening, but I want to properly explain what is actually going on so you can really understand for yourselves what it is. Now, rainbows are a spectrum of light, which is from the light from the sun. The first observation that you can make about rainbows is that they're always on the opposite side to the sun. Now, the reason for this is because they come from reflections in water droplets, so they actually have to reflect in order to get back to you. So they go from the sun, reflecting the water droplets on the opposite side of the sky, and then bounce back towards your eyes. Now, the effect that we're going to discuss does happen in all water droplets, but for reasons you'll see is the reason you see the rainbow on the opposite side of the sky to you. Now, one of the first things that happens to the light when it's making a rainbow that we need to understand is that when light enters something that's more dense than something it was travelling through before, it turns and slows down. It turns because it's slowed down. If you can imagine, any solid surface running towards something, and then if it then hits, say, edge first on something that's more dense, it'll turn towards it because it's been slowed down on that corner first. So light behaves much like that. In fact, if it was going to go through just a piece of glass, any piece of glass, it will have incident light, in this case from the sun, and the light, as soon as it reaches the surface of the material that's more dense, it will turn while it's been slowed down, and upon leaving the material that it's just entered and going back to the original density it was in, it will speed back up and turn back to the angle it was originally pointing at. Now, this is important because water droplets have what's called a higher refractive index than air, and all that really means is that the material's more dense, so it makes light slow down when it enters it, and that's the only thing that's really important about that. The refractive index is just a number that's assigned to it that we use in the maths so that we can understand the angles, and when you can properly work out the definitely correct angles that light will go through when it goes through something that's more dense. The term doesn't actually mean anything to a layman, say. Now, on to what actually happens to the light when it's making a rainbow. So, in the air, in the atmosphere, all around us, there are lots and lots of water droplets. It's well known that the Earth's humidity is quite humid. So, we have these nice droplets of water. We have incident light from the sun. And using what we just talked about, when the light reaches the water, it turns because it's slowed down, and partially it is transmitted back out through the other side, and as we say, it speeds back up once it comes back out of the water and turns again. But the thing that actually makes the rainbow in the first place is it reflects off the back, and light can do this when it reaches any surface it has potential to reflect, which is how we see everything. If light bounces off things and it reaches our eyes. So it reflects off the back of the water droplet and then comes back out the other side. Now, the reason this is able to make a rainbow is because when light bends and turns through something that's more dense than it, the different energies that are there in light, so all the different colours of light are all different energies, and the higher energy you are, the more it causes you to turn, which means when light goes into something that's more dense, it splits up a bit. So it makes a little bit of a spread effect, and in the spread effect you'd be able to see the individual colours, and then you give it a bit of time, i.e. it bouncing around in this water droplet, it spreads out even more, and then when it finally does come out, you can end up with the light rays that come out are all split up into their individual colours in the order of what energy they are, i.e. a rainbow. Now, on to the reason that you only see an arc in terms of rainbow, because as I said at the beginning, this effect happens in all water droplets that are big enough to allow the light to split up. So, in which case, why doesn't the whole sky look like a multicoloured barcode, essentially? Because you would be seeing the light split up from all the different water droplets. And the reason is, when the light comes in from the sun and bounces around and comes back out and is emitted from the water droplet, it makes this angle here. Now this angle is exactly the same every single time. And this angle, because of some maths, happens to be 42 degrees. And that angle, you can work that out because just by knowing the density of air and the density of water, and then going, well, I know that light bends this much exactly when it comes in, and then I know it's a sphere essentially, and it bounces off the back, so you can go, right, I've worked out that angle, it's 42 degrees. Now, this angle means that only certain water molecules can shine their light at you. Because, if you think about it, you'll only be able to see the light that comes from a cone away from you. And if you think about it, all these angles are made up in a cone out in front of you, because they have to be on the same line around you according to your eyes for you to be able to see it. Otherwise it doesn't make up that angle of 42 degrees with you, and if it doesn't make up that angle, then you're not going to see any light. So if someone stood just to the left of you, they'll see a slightly different rainbow to you because the angles won't quite match up perfectly with your eyes and theirs. And if you're now thinking, well, that doesn't really make sense, why is it just an arc? It's not, in fact. It would actually make up a full circle were the horizon and the Earth below it not in the way. In fact, astronauts from space have taken images of full circle rainbows because they're able to see the entire cone of light that's pointing directly at them. So given that the effect happens in all water droplets, it can in fact happen in all kinds of water droplets. So there's things such as fog bows, which are the same principle, except in fog the water droplets are too small to give the light a chance to disperse properly for you to be able to see a spectrum when it comes out the other side. So you'll still get an arc of more intense light that's being shone at you in a cone, but you don't get the colour spectrum because it's not had time within the water droplet to spread out far enough. Now you can also have double, tertiary and quaternary rainbows, which are the light bouncing around within that water droplet, because in the atmosphere water droplets are not a perfect sphere. They're moving around, there's wind, there's all sorts of things which squash and warp the shapes. Now, and that means that when light does bounce around, it can bounce around multiple and several times. And it's this effect that leads to double, tertiary and quaternary rainbows. Double rainbows are common enough to be seen, and all that is the light making that same 42-degree angle, but from a different point on the water droplet. So the light comes out of that water droplet exactly the same way as it did before, but from a different place. So you'll see the more intense primary rainbow, and then some of the light may have got a chance to bounce around more. Obviously that is much less likely, so it'll be a lot less intense, and you might get a chance to see, on particularly bright days with a dim background, a secondary rainbow. And this is possible for tertiary and quaternary, so third and fourth order, i.e. the water bouncing around even more times onto the third and fourth loop around the water molecule. However, that is always far too dim to be seen by a naked eye. You can prove that they do exist. In fact, it was proved in 2011, which is very late, for rainbows especially, that tertiary and quaternary rainbows do exist, we're just unable to see them because they're too dim.